Yeah.
Sorry, insane. That is a nice diagram.
That's crazy.
Clark University.
Are you able to adjust that? Is that one of those applets that you can?
No,
Okay.
it's just a-
All right. So what Euler had to do with this guy? Take a look up here at my image.
What is that?
Did Tufts, is this moving?
Is that a hockey something?
No.
What's the glasses?
What's that?
It's like a mask.
It does look like a mask. This is the bridges of Konigsberg.
Bridges of Madison County.
Could have been in Madison County. I don't think they had 7 though. So this is Konigsberg, and what Euler did was take the map that looked a little confusing and turn it into something that was less confusing.
Even more confusing.
What's that? What do the red dots represent?
Bridges. The intersection.
Intersections? Okay, how else could you describe it?
The place where they meet twice.
Place where what meets twice?
Their paths.
Where the paths meet twice? Okay, tell me more. On the map, what would the dots be?
Oh, like where you go again. Like.
So like
Triangle.
The triangle?
You connect all the points and it's a triangle.
If
Yeah, we're
you,
past
so like the beginning points.
I see
Something big
3.
square.
Where are you?
No, Mike, if you connect the bottom, the top, and the point.
you connect the bottom, the top,
And
and
maybe have the middle be like the midpoint.
No.
so go
Oh
here.
wait, is it like the 3 points are collinear and the fourth one that's awkwardly out is the inside?
No, the 3 points don't look
No, we're the center. I like when you think it, but your triangles aren't going to help you here.
What did you do?
What you do?
Then it's squares, obviously.
Well, it'd actually be a kite.
It brought a pair.
Oh, yeah. Okay. Oh, okay.
Because you
Actually, I
have
thought the
these
first
two
time I thought you literally-
congruent sides and these two congruent
I heard a
sides.
panda.
Nothing.
It's a parrot, Kelly.
What, a parrot?
You can see the bridges on here?
Yeah, it's the other
Yes.
ones.
Okay, you can see the yellow bridges.
Maybe one of them's like a certain point.
You can see these big white areas. Those are the land masses on your map.
Yeah.
And so the dots just represented the landmass.
Okay.
The dot was a place you could get to. It could be anywhere on that landmass, anywhere on that island.
Okay.
But you could get there by going across this bridge or going across this bridge, any of these bridges, any of these 5 bridges. That's a landmass and a landmass and a landmass. And these lines right here, which we call edges, these edges are the routes that you can take. You can go from this town, kind of like, girls, hi. I know you're mesmerized. Kind of like if you look at a map of all of the locations that Delta Airlines flies, or all of the places that you can fly out of Newark Airport. Well, you could go to Philadelphia, you could go to Washington D.C., and so on and so forth. So these are just the different places that you can travel. You can go across 1, 2, 3 bridges. From here, you can go across 1, 2, 3, 4, 5 bridges, and from here you can go across 3 bridges. This one is actually, like I said, it's impossible. You cannot go from one point or one vertex to the next and touch every single edge or every single path one time. It's impossible.
Then it works.
They could have made another bridge. That would be the architect's, that would be the architect's approach to solving the problem. The physicist's approach would be, I could time travel, or I could teleport from one place to the next and get it done.
How about we just take a boat there and ferry?
Let's see, what other approaches could you take? You could fly. You could destroy a bridge. If you destroyed a bridge.
Wait, so this is the project like not done?
Yeah, it's not bad.
They showed up with half the brochure empty.
Yeah. Like,
How many are there?
How many vertices total are there in the first?
Watch out.
4 vertices, okay.
Okay, and is it traceable?
Yeah.
So we're clear on odd and even vertices. You're looking at the first image, A, and you're looking at the top right corner. Is that an odd or an even vertex?
Even. Odd.
top right.
There's two of them.
There's two paths going to that point. There are two edges going to that vertex. So that top right is an even vertex, as is the bottom left, or top and bottom, if you're not thinking left and right. Okay.
Alright, B. There's three
Yeah, there's three.
and three.
Yeah, it's on three. Oh my god.
Is there two?
There's
I don't know.
Isn't there 4 evens? There's 4 evens.
Wait, there's four even?
There's 4 evens.
This one also goes there, and that one also goes there.
The middle one's
Wait, I have no idea what you're saying.
3, 4, yeah.
There's 4 evens.
Oh, you're right.
3 odds. Is it traceable?
Yeah.
Isn't it 2 odds?
Yes.
Only 6 vertices.
Yeah, there's 2 odds.
Oh. I just saw that.
This was traceable?
Yeah.
Wait. C or B?
You would go around and then you would.
B.
Who can demonstrate its traceability? All right, show us.
What's the shape?
Where's it going?
I'm just making sure. Like, is this what it is?
It's
No, you have a
hexagon.
pentagon there. You need a hexagon.
Oh, this is the first figure? Like, is it like?
Yeah. Yep.
So I have this one. This one. This one.
If I trade the points, and when you connect it over the different number.
Yeah, I can do that.
Just gotta do it.
Okay. Next.
C.
There's 3 evens.
Yeah.
Wait, I'm kidding. 2
So
evens.
there are.
Two odds.
I mean,
Wait, there's 3
Why?
odds. There's 3 odds.
1.
Yeah, the line coming out at the bottom.
3.
Oh, that counts too?
I wouldn't.
Oh, wait,
So 3. Yeah, that one looked like 4. And then you
Wait,
get
hold
that
on.
extra line.
This is even. This is
No,
even.
there's 4 odds.
There are?
There's 4.
Yeah.
There's 2 even. I have 2 evens so far.
3. Oh, she's right.
Which one's the fourth?
There's
The
3. Yeah,
one
there's
at the
2
bottom.
evens.
Oh,
There's 2 even and then 4 odds.
Anything
Yeah.
that
Yeah, there
connects
is.
to a vertex. So you're standing at a vertex, you're saying, how many roads can I go down?
Wait, how are there 4?
Just look at it.
3 odds. Which one?
There's 4 odd versions.
I see. Because it's diamonds.
Right, so here in C, you have, from this vertex, you have 1, 2, 3 ways that you can go.
Is it traceable?
So that's odd.
No.
Over here, you can go 1, 2, 3 ways, that's odd. Here, you can go 2 ways, that's
Wait,
even.
no.
Here, you can go 1, 2, 3, 4, 5,
Does that
that's
count?
odd. Yeah.
Otherwise, you have a point.
It does.
Wait, how? How do you have
But if you're standing here, you can go down that way, 1, 2, 3, 4, 5.
Everything else.
So this was odd.
That's all
Alright, what about D?
Even. That was odd, and that was odd. What's that one?
2 odds.
No, there's 2 odds.
Yeah.
There's 2 odds. And 4 even. 4 even.
What's this one?
4 evens.
So there's a 4 and 2?
Good job.
4 and, oh, and this one's off 2 and 4. Okay.
Oh, you already did these?
Yeah, was that E?
Good job.
Okay,
Now we're on to E.
There's
4 odds.
4 odds.
Let's do it.
2 evens.
Three.
Where's the third even?
Oh.
In the middle.
There's two even.
Like the, I don't know where does the third odd?
There's a bird, isn't it?
It's
There's
like-
not.
I know.
There's two even.
Oh.
I don't know how I feel about that one.
What's wrong?
Because that doesn't count as a point because there's not an answer. I don't know.
Mr. Tufts.
Yeah.
E, you know, on the right side, there's no, like,
Should
point
there be?
with a-
There shouldn't be.
Should it be there,
I
or?
think we can count that as a verse.
Oh, okay.
So it's not this.
Three. Even.
It's like
That means
even.
And no, right?
this is one. This is one. I think there's two even.
4 and 3, we said.
I think there's two even.
2 even, 6 odds.
Yeah.
And now?
And 2.
Even.
Wait, that looks pretty good. Better than mine.
G?
Gee.
I think there's four even.
1, 2, 3, 4.
Wait, but then how do you count? The circles has, the two parts of the circles is two, right?
Yeah, that's one. Okay.
There's 4 odds.
I'd say 6 odd. There's 2 even, yeah.
I want to say there's four even.
I'd say there's 6 odd. I have 6 odd.
Yeah, 4 even, 6 odd.
Where's the fourth even?
The two bottom points of the circles.
There's only.
There's 4.
There's four lines connecting out of it.
Oh, yeah.
So is it 4 and 4?
I'd say 6.
Why 6? Wait.
Wait, 6?
It's 4 and
Why
4.
6?
Gotta
Yeah.
be 4.
That's what I thought. So I could someone say 6.
We're at 8 total, right?
Yeah.
Yeah. Alright, 8
That's even.
there.
That's even.
They're all even.
No.
No.
No. You have 2 odds and 3
There's
evens.
odds 2 even.
Wait, 3?
3 even.
Oh, there's 3.
3 evens.
And 1 odd?
2 odds.
Two odds. Yeah.
Here's an even. Here's an even. There's an even. There's an even. And there's an even. They just
4
five even.
odds.
You guys just got.
4 evens and 4 odds.
Wait, no.
No, 5 evens and 4 odds.
Start counting from P backwards.
5 evens.
5 even.
I have 5 evens.
Wait, but this counts as. Oh.
There's an
Wait,
even.
just.
And it's not traceable?
No.
4 odds.
Odd. Yeah, you're right. You see what I did there? Good job. That's even. Everything's even.
I know, I can't see.
Two odd, 1 even.
How many dots are on it?
Great question.
One.
Wait,
Even.
the ones that all
even?
Yeah.
1
So
even?
4 and
Like
0.
Yeah, because it's not two.
Yeah.
Even.
That kind of.
It's a 1, yeah.
One line.
It's 1 line.
So one odd.
But there's 2 sides. I don't know.
That's what I was
I
saying.
think it's 1 odd.
No, but you're.
Sides.
Yeah.
It's one line connecting around 1 point.
Just kidding.
So it's 1 odd.
One.
For what?
The circle is 1.
There's one odd.
Because that's like 1 line going around that 2.
So it's like
Two
it
that
has.
How many points in there?
Wait,
1, 2, 3, 4.
Okay, you make the same arguments and
You're
go
not
on.
that. Yeah.
And
4
those
and
are all.
1, 4 odd, 1 even.
Yeah.
How can you say that?
There's 4 odds.
You guys, this one actually has like.
Is yours more?
It's one line. You're making the
I'm
argument.
just trying to speak it out.
Okay. How many does N have? 1, 2, 3, 4, 5,
7.
6, 7. And it's O traceable?
No.
And then P?
Yeah.
Because I don't usually drink coffee.
It's like that's
I disagree with L.
Yeah, I was just about to say, how can you say that?
Yeah, I don't.
How can you be controversial with L and
I say two odd. I don't know why.
yeah. LM. Hey.
It depends on how you look. Because if you look at it from the
Come on.
vertex, it's two lines coming out from the
Do it.
vertex. But if you look, yeah.
Every point you stand on
We can go this
on
way
M
and then that.
has two ways
Do
you
the
can go.
explosion, do the explosion.
That's terrible.
Here's that.
Wow.
So which one you
Sure,
stand
it's
on,
high.
the left or right?
What
left or
high?
right?
Wait, why would
Oh.
L be?
One of them is right.
Are you ready for the presentation?
Yeah, but look, you.
We don't even know what we're doing, but okay.
It's okay. We're going first.
L has 1 point on it.
Yeah, but.
How many ways can you go? If you're standing on that one vertex, how many ways can you go?
2.
You can go 2 ways. So
Gosh,
is that
so
odd or
hard.
even? You can go 2 ways.
Wait, you said how
Yeah, but
many
you can also
lines
go the
come
other
out
way.
from it? Only one line is there.
Yeah.
But there's still two coming out from it, even if there's one
Yeah.
line.
You can
You
go
still go 2
right
ways.
one and then left one.
But
So me and
it's
Shreya
one
were
line.
running.
I agree with you, Kelly.
But even if you like, if you think about like a straight line, like you can still go 2 ways on it.
So then everything's wrong. Everything is that
Well,
way.
if you think about like.
Wait, no, wait, one
Wait,
even.
Mary, wouldn't that be one odd and 0 even?
Yes.
One
No.
even.
I mean, one even and 0
One,
odd.
1 even, 0 odd.
My thoughts are that.
Stop.
No, like.
Which one do you think's better?
Who is it?
Yeah, 1 even.
Yeah, like this shirt.
Yeah.
I just got this one.
Probably this
All right, so you have all that data up
You
there.
could zoom this one like that. Get a good-
Now it's a lot of fun to look at a network and trace it, especially now that we have styluses and we have these iPads that you can draw on and color and make it pretty. But it's not necessarily the most expedited way to figure out the network's traceable or not. So to take a look at your odds and your evens and the traceability. Is there a way to tell whether or not a network is going to be traceable or not? Look at the data and see what it's telling you.
There's more, only 2 odd. There's more odd vertices, you can't trace it.
Alright, the more even,
No, but none of odd vertices.
if there's more even than odd, you can trace it. Yeah,
If there's
if there's more even than odd. Yeah.
Yeah.
There's more odd.
No,
If there's like
even.
the more
I know,
than
but
2 odd
Drew's right,
verses,
yeah.
it won't trace.
There's more odd vertices.
Well, what was I?
What about I was at
I was a
9.
straight line.
So what are you guys looking at? Are you looking at the non-traceable ones, or are you looking at the traceable ones?
The non-traceable ones. Well, both.
You're looking at both. So let's just focus on one of them. Let's look at the nons first.
Okay.
The non-traceable ones. Nons. Right here. Right here. Right here. Here. Here.
You made me afraid.
Here. Here.
They all have 4.
Did we get 8 and 8?
Never mind.
Oh no, it's 7. It's 7 and 9. That's right.
Wait, that's so cute.
So, is there anything that they have in common? Look at your odd vertices. Anything the same?
They're all
They all have 4?
They're all
even odd vertices.
they're all more than 2.
even odd verses.
They're more than 2, and an even number of odd vertices?
Yeah.
Okay.
Ew.
What about the even vertices? You got
It's all over the
0, 1, 2, 3, 4, 5. So we have a lot of different number of even vertices. So that doesn't help us. But so far it looks like for non-traceable networks have, how'd you phrase it? An even number of odd vertices? Okay. So that's one distinguishing characteristic we can pick out. Now what about the yeses?
I didn't do anything.
Oh, there are a lot up here if I just open my eyes, okay. Here's your yeses. Yes, and a yes, 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 and yes. Anything in green for traceable networks?
All the odd vertices are less than 2.
Traceable networks, let's see.
Even number of
Odd
odd
vertices, even vertices. Again, does even vertices tell you anything? Did we get a consistency in the even row? 4, 7, 6, 1, 0, 3, 4. So again, nothing with the even vertices. What about the odd vertices?
It's 0 or 2.
It's 0 or 2?
But yeah.
Yeah.
What's that?
I thought O was a yes.
So we got zeros and we got 2s and nothing else. Traceable networks have, oh, we have kind of conflicting things here, right? Are 0 and 2, does this differentiate itself or set itself apart from this definition?
Yes.
Like, could we interchange the two things? Could I say non-traceable networks have either 0 or 2 odd vertices?
No.
I can't?
No.
Oh,
Yeah.
because we had 4 and we had a 6 in there. Okay.
They can have 0 or 2,
But
but
yeah,
that's not
that's
what you're
just-
limited
it's
to.
just
You're
not
not
limited
limited
to
to that.
Okay, so we could, but it's not exclusive. Could I say traceable networks have an even number of odd vertices?
No.
Yeah, but it has.
Well, yeah.
But there's a limit. Okay. So which is a more restrictive definition?
Traceable network.
The traceable networks? Because this says you can only have these two things. So there's your definition. What Euler discovered. 300? No, 1746, 1750. 260 years ago? Is that right? So that's what he figured out, that if you're going to have a traceable network, which happens all the time, this is in the way email is structured, the way security functions on PayPal or things like that are structured, a lot of the wiring inside your home, hopefully, unless you're in my house that Jim built, that's going to fall under these network rules. Whole set of mathematics based on this. 0 or 2 odd vertices is going to determine whether or not your network's going to be traceable or not. Kind of that up there. That's pretty cool. All right, what can I do here?
Let us sleep.
Do you want some homework answers?
No.
No, you have to go on you right now. I'll give you homework answers. Were there any problems that confused you or anything in the chart, the, what did I call it? The flow chart that you didn't understand?
No, they're all pretty self-explanatory. I don't think we need to.
Let me give you answers real fast just to make sure we're on the same page. Number 4 was first.
Yeah.
Angle D. Okay. The side parallel to AB is DC, and the segment congruent to AC is BD. What are AC and BD called for this polygon?
Bases. It's bases. Base 1, base 2.
AC and BD.
No, you did the diagonal.
AC.
AC and BD.
It's diagonal.
AC and BD are
Oh,
diagonal.
yeah, bases.
Are they like a specific kind?
What's that?
I don't know. Are they a specific kind of diagonal?
Are they a specific kind of diagonal?
I'm sure they're diagonal.
No, because he asked for the name of them, so I was like,
No, they're just called the diagonals of the polygon. And I think it's a little different. Typically, we come into this class thinking diagonal is any line that does that. A diagonal could do this, and a diagonal could do that. All a diagonal is a segment that connects one vertice to the next, or one vertice to another. It doesn't connect adjacent vertices. That's the definition of a diagonal. 11. Value of C. The value of x is C. The value of x is 13. What's your property in number 11? This is a parallelogram. They're giving you markings on what? They're giving you markings on the diagonals. Property of a parallelogram is that the diagonals do what?
bisect each other.
They bisect each other. 12. You have a kite. Properties of a kite. Michelle, what's property of a kite?
What do you mean by that?
One property of a kite. One characteristic. One redeeming quality. One attribute.
What the, no lines are parallel?
No lines are parallel. That works. Is that always going to be the case?
Their diagonals are perpendicular.
That is true. Their diagonals are perpendicular.
They're adjacent.
I don't know about that. I got to think about that parallel
Says it on
one.
here
Then no sides are parallel?
the parallel sides.
No parallel sides. Yeah, I want to see why that actually happens. Okay, so the diagonals are perpendicular and what else?
The sides are
And the adjacent sides are congruent. So you get two pairs of congruent sides. They're just not opposite from each other, like in the parallelograms. So GF is 5, and the measure of D at number 13 is 122. What else do you get in a kite? Any other congruencies?
Oh, there's one pair of congruent.
There is one pair of congruent angles, which you needed in number 13. D and G are congruent. And number 14, this is a rhombus. Characteristic of a rhombus, Julia, is what? One characteristic.
All four sides are the same.
All four sides are the same. Good. Julianne, what's another characteristic of a rhombus?
Diagonals are perpendicular and their angle bisected.
The diagonals are perpendicular, and what angles are bisected? Yet again?
All of them?
Okay. Sure. The vertices are all bisected. So MRN, right, where the diagonals intersect, is 90. That angle measured for 15RN is also 12. And the number 16 POM is 62. I don't think I gave you 17, right? That's a silly problem. Number 18. This is a parallelogram. JML is 109. What property of the parallelogram does that satisfy, Catherine, in number 18? The JML is 109. Opposite angles are what? Equal or congruent. Good. They have equal measures, so they're congruent. JK is I'm looking at KL. Okay. JK has a measure of 6. Ariana, why does JK have a measure of 6?
Because opposite sides are congruent.
Good. And number 20, KLM has a measure of 71. Jordan, why does KLM measure 71?
Because when you have to add the interiors equal 360, since two of them are 109, the other two have to be 71.
That works. Is there a shorter way, Kelly, to get to 71? You did the same thing?
Adjacent angles are supplementary.
Your adjacent angles are supplementary, so that cuts your work in half, but either way you get the point across. Good. In number 21, this is a rectangle. Khadijah, what's one characteristic of a rectangle? anything you know about a rectangle? Not necessarily. That's the other half of the parallelogram family. All angles are congruent. So there's where the parallelogram family splits into the equilateral half and the equiangular half. Equilateral half is the rhombuses, equiangular half is the rectangles. When they get back together and they mend their differences, that's where they make a square. So in DF, you have, or in 21, you have DF and EG. What property, Suraj, of a rectangle could you use in number 21?
It's like, wait, what was the answer to it again? I want to check if I got it right. Yeah.
Answer was 21,
Well, I got that wrong.
or 21. What do you know about DF and EG?
They're congruent.
They are congruent because in a rectangle, the diagonals are congruent. In a rhombus, the diagonals are, Tamia?
Perpendicular.
Perpendicular. And the angle bisector part, yep. But in all of these, in all your properties, you get some things that are the same and some things that are slightly different. In terms of the sides, in terms of the angle, you get congruencies, or you're going to get perpendiculars. In 21, for the rectangles, you get congruent diagonals. In rhombuses, you get perpendicular diagonals. In 22, you have EDF, and you have DFG. Shreya, what's the relationship between EDF and DFG?
They're congruent.
Because
The diagonals, like it's the diagonals, the angle bisector.
if this was, what kind of figure it would be an angle bisector?
Yeah.
It would be, if it was a rhombus, they would be for that reason. These angles are congruent, but it's not because the angle was bisected. Anybody know why these angles are congruent? Think of chapter 2.
Oh, they're corresponding because of parallel lines.
Close.
I mean, they're alternate interior.
They're alternate interior angles. EDF and DFG are alternate interior angles. And in 23, the answer is not 23. The answer is 34. You have DE and GF, and DE and GF are going to be congruent because this is a parallelogram. And so your opposite sides are congruent to each other. In 24, do you have enough information to tell that this is a parallelogram? Ganna, what did you say? Enough information to say it's a parallelogram?
Yes.
Why did you say yes?
Because they have the correct congruent markings.
On what?
Opposite angle, congruent angle markings, opposite curve. What is it?
You have all the information there. Just put it together.
The opposite angles are congruent, which makes it.
There you go.
Yeah.
Opposite angles are congruent. That's enough. 25, enough info? Not enough info. This is probably a what? Or you have enough information to say that it's a what? Or 25. A what? A kite. You have two pairs of congruent sides, but they're adjacent to each other. 25 is a kite. You may shut your iPads down